Hi, welcome to our 9 a.m. press conference, The Changing U.S. Snowpack. Our presenters this morning are Sagar Tamang from St. Anthony Falls Laboratory and the University of Minnesota, Twin Cities. Zubin Zhang, the University of Arizona. Amato Evan from the Scripps Institution of Oceanography, and Donal O'Leary from the University of Maryland, College Park.
Hi, good morning. My name is Sagar Tamang. I'm from University of Minnesota, and today I will be talking about how snowfall-dominant regimes are changing globally. Before I start, I would like to mention my co-authors on this work, Dr. Ardeshir Ebtehaj and Dr. George Huffman. So currently in the world, about 2 billion people depend on water which is derived from snow melting. And with global warming, we found that the snowfall proportion across the globe is decreasing, thus risking their life. In this study, we use 4 different measures to track how the global snowfall is changing during the period of last 4 decades, which is from 1979 to 2017, which are wet bulb temperature, potential snowfall areas, snowfall to rainfall transitional latitude, and snowfall to precipitation ratio. First, I want to talk about wet bulb temperature. It's a parameter which takes into account the effects of humidity and pressure on air temperature, and is a better identifier of phase of precipitation, which is like it can classify between snow and rain better than the air temperature. The figure you see on this slide is a time series of the wet bulb temperature during the last 4 decades, with year on the x-axis and wet bulb temperature in degrees Celsius on the y-axis. The top row shows you the time series for Northern Hemisphere land and ocean, whereas the bottom layer shows you the time series of Southern Hemisphere land and ocean. The 3 different color lines are the results from 3 different Earth system models from Europe, Japan, and the United States. In our study, we found that the wet bulb temperature has actually increased at the rate of 0.32 to 0.35 degrees Celsius over the Northern Hemisphere land, whereas it also increased at the rate of 0.34 to 0.41 degrees Celsius per decade over the Northern Hemisphere ocean. We also found the wet bulb temperature has increased at the rate of 0.15 degrees Celsius per decade over the Southern Hemisphere land. However, no significant warming was found over the ocean. Using the information from wet bulb temperature, we were able to classify between the snowfall areas from the rainfall areas. And the figure on this slide is the same as the figure on the previous slide, only the y-axis has changed. Now the information here is for potentially snowfall areas in million square kilometers. We found that the over Northern Hemisphere potential snowfall areas have actually decreased at the rate of 0.44 to 0.56 million square kilometers per decade, which is roughly the size of the state of California. And over the ocean, it has actually reduced at the rate of 0.28 to 0.39 million square kilometers. We also found that potentially snowfall areas is actually expanding in contrary to what was observed over the Northern Hemisphere in the Southern Hemisphere at the rate of 0.53 million square kilometers per decade. We also tried to track the average latitude where this change was happening, and we tried to see how that latitude is moving upwards or downwards during the last 4 decades, which is shown here on this slide. The y-axis is now the average transition latitude that separates the snowfall area from the rainfall areas. On the top row is for the Northern Hemisphere, and the bottom row is for the Southern Hemisphere. We found that over Northern Hemisphere, average transition latitude is actually moving poleward. However, on the Southern Hemisphere, it is actually moving towards the equator at the rate of 0.21 degrees per decade. So what these 2 movements in 2 different hemispheres are causing is the rainfall regions are actually expanding and shifting towards the North Pole during the last 4 decades. We further combined this data with the precipitation data from multiple sources, and the results are shown in this figure. Each rows are the results from 3 different Earth system models, and the left column is for the trend in the snowfall to precipitation ratio. All the red areas and the orange areas are the area where the snowfall is reducing over time. And the right column is for the statistical significance. So all the areas with green, we have higher confidence in the obtained trend. We found that during the last 4 decades, between the latitude of 40 degrees to 80 degrees north, snowfall to precipitation ratio has actually decreased. by 2 to 8%, whereas we also focused on different mountain regions around the world, such as high mountain Asia, Colorado Rockies, and Swiss Alps, and we found that these mountain regions are also experiencing significant loss in the snowfall precipitation ratio at the rate of around 1 to 3% per decade. So to summarize, in the northern hemisphere, we observed an increase in wet bulb temperature, thus decreasing the potentially snowfall areas over the last 4 decades. And we also found that the two hemispheres' average transition latitudes movement is contrasting to each other, with the northern hemisphere transition latitude moving towards the North Pole, whereas the southern hemisphere transition latitude moving towards the equator. And we further found that the data from 3 different Earth system models agree that the snowfall to precipitation ratio is decreasing worldwide. I also have included my contact information here on the slide, and I have an oral presentation on Friday at 4:45 if you'd like to know more about this. Thank you.
Good morning. Today, I'm going to discuss the snowpack change from 1982 to 2016 over conterminous United States based on the paper just published today, co-authored by myself and my group members, Patrick Broxton, doing the field work in the picture, and Nick Dawson. We have developed the first daily 4 kilometer or 2.5 by 2.5 snow mass and depth data sets from 1982 to 2016 over conterminous U.S.A. canals. For example, this figure shows the annual maximum snow mass climatology. Most of the snow mass is located over western U.S. in the mountains, and the peak snow mass over canals is about 18 times the average annual flow of Colorado River, as measured at Lee's Ferry. This figure shows the significant linear trends of annual maximum snow mass. Most of the areas, obviously as indicated by the white colors, do not have significant trends, particularly over eastern U.S. Over the west, however, the annual maximum snow mass decreased significantly by 41% on average for 13% of snowy areas. If we add those areas together, they represent the size of South Carolina. This figure shows the significant trends of snow season length. Again, most of the areas do not have significant trends. But over both the western and the eastern U.S., we see areas with the shortening of snow season, even though there are also small areas with longer snow seasons. On average, snow season was shortened significantly by 34 days on average for 9% of snowy areas over canals. If we add those areas together, they represent the size of Virginia. The question is then, what are the primary drivers of the snow mass change? In this figure, we show the time series over western U.S. Top panel, the April 1st snow mass. We use April 1st because that's the date water resources managers use in the West. Middle panel shows the accumulated precipitation from October to March, and the bottom panel, the average temperature. Both the snow mass and the precipitation show very large year-to-year and decadal variabilities. In contrast, the temperature shows a significant trend due to global warming. Both temperature and precipitation are needed to explain the snow mass variability. However, considering temperature alone can only explain 25% of the variability of the snow mass here. Furthermore, it would exaggerate the Omi effect on snow mass decrease by a factor of 2 or 3. This map shows the locations of all the ground measurements used to develop our data set. Each black dot here represents a volunteer, and there are more than 10,000 volunteers across the U.S. making the snow depth measurements. Over western U.S., the white squares and triangles represent the government network for snow mass and depth measurements. The question is, do these point measurements themselves represent the snowpack decline across the whole western U.S.? To address this question, we compute the trends of annual maximum snow mass at government sites and collocated 2.5-mile grids of our data, and the results are very similar. For example, their median trends are minus 2.8 and minus 2.9 millimeter per year, respectively. However, results from those locations do not represent those using all snowy grids of western U.S. above 5,000 feet in elevation. I use 5,000 feet because all those government sites are located above this elevation. In fact, the median trends using all the snowy areas over western U.S. is only minus 0.5 millimeter per year. Here is the take-home message and my contact info, including my email, cell phone, publication published today, university news release, and my oral presentation information tomorrow. Thank you.
Okay, so while I'm waiting for this to change, I think it changes on its own. Yeah, great. My name is Amato Evan. So I'm going to talk about some work that is being published, that actually was just published like 30 minutes ago in the Journal of Applied Meteorology and Climate. And what I'm going to ask is how healthy are our winters? So if you look at the picture on the left, this is the Sierra Nevadas. And this is a satellite image from April 1st, 2002. This stuff over here, these are just clouds, so don't worry about these too much. But what you can see is mountains, the Sierras filled with snow, looks pretty darn healthy, looks pretty good. Shift to 2015, the year of lowest snowpack on record, potentially in the last 400 years at least. Same date, April 1st, and you can see not so much snow in the mountains. And also, it's just a lot more brown in the foothills too. So I would say on the right, that looks like a pretty unhealthy winter. And so if you put those together, I would say mountain snowpack. How much snow there is in the mountains, it's one way of gauging how healthy our winters are, but I think it's a reasonably fair measure. And in the West, this matters a lot because for society, so much of our fresh water is stored up in mountain snowpack. It's hugely critical. And then as Donal's going to talk about in a little bit, it really makes a big difference as far as the ecology and particularly fires too in the West. So detecting trends in snowpack is difficult, as Yuban was just discussing. This is an image from 2017. In February, this is the Lake Oroville Dam spillway basically bursting open and causing a lot of erosion because there was just so much precipitation, so much snow in the mountains. So, we looked at 2002, good year, 2015, amazingly horrible year, 2017, like just a lot more snow than anyone expected actually, and like a really healthy year. So the way that I approach this problem is to use this observational network of snowpack. And what this is a network of stations up in the mountains, basically covering every major watershed in the western U.S. And what this comprises of, basically a big rubber pillow that's filled with antifreeze. And that pillow measures every hour continuously, really, the weight of the snow that's on top of it. And so it's actually an incredibly accurate measure of snowpack. And so that's what this plot is here on the left. This is the time series, in the dark blue line, the time series of snowpack from October through June. This is the way that we kind of think of the calendar year, starting on October 1st. And what you see is from the same site, by the way, in Idaho. And what you see is a gradual buildup of the snowpack over the year, and then a rapid decline, which it coincides with essentially when we get a lot more sunlight and when the storms essentially kind of migrate out of the western U.S. And so the thing that, that I did, my unique contribution here is essentially finding a mathematical function you can use to describe this curve. This curve is kind of noisy. If you want to study climate, that's not really ideal. I don't really care about these little blips. I want to know the general characteristics if I'm interested in climate variability. And so this curve is slowly, this mathematical function basically describes this curve very well, captures this rapid decline in the springtime. And then what it allows me to do is analyze the function, the variables in that equation, rather than analyzing the data, which is a little bit more noisy. So there are a bunch of results, but the two big ones, the two robust things that I find across the western U.S. looking over the period 1982 through 27, actually I just updated it with last year's data last night, so through 2018 it's the same story. Thing number one, result number one, the annual cycle of snowpack is being squeezed on both sides. In other words, the summer is basically coming earlier, fall is coming later, all right? So snowpack is just being squeezed in. The other major finding was, and this is a little more subtle, the annual cycle of snowpack is becoming more bell-shaped. So, I'm sorry, I should have explained on the previous plot too. This is what we would expect in a kind of a healthy winter. We see that gradual decline in the gradual buildup and that rapid decline of snowpack. And what I'm seeing in a lot of these sites is that this curve is becoming shifted. It's looking more like a bell, less skewed, less pushed off to the right. And what that is snowpack in high elevation sites has this really skewed shape. Snowpack in lower elevation sites has this more bell shape. And in fact, so one thing I would say is that essentially the mountains, in effect, they're kind of shrinking. They're getting a little smaller with regards to how much snowpack. And this is a result, interestingly, that has been described previously, but only in theory, only in model simulations. This is something we expect over the 21st century. As far as my understanding is, this is the first time that somebody's actually shown this result with observations. So the net result, if you put all these changes together, there's been a decline in springtime snowpack. And this plot right here, the blue line, that represents, on average in the western US, this is what snowpack looks like. Again, if you average all these stations, all this data, and then instead of looking at the actual data, look at these mathematical functions, you see this gradual buildup, the rapid decline. And the change over the 36 years, and if you add another year, it looks essentially the same, is that all of those changes are being loaded into the spring season. So the biggest change in snowpack is actually coming in April, May, and June. So how healthy are our winters? Well, I would say that western mountains are shrinking, right? That whole thing, like snowpack is looking more like it is in lower elevations and less like it is in higher elevations. The season is being squished. Essentially, our winters are getting shorter. And the spring snowpack, that's where we're really getting it. It's all being pushed up. The spring snowpack is in decline. So I would make the argument that our winters are getting sick, and we know the reason why. I mean, it has to do with it's global warming. It's rising temperatures, and that's just as the only logical explanation for what's happening. So I have a poster describing some of these results. That is right now. But I'll be there at 11 o'clock. And then there's my contact information. Thanks.
All right, folks, thank you all for coming. Thank you for my colleagues here. And I'd like to acknowledge my co-authors on this work, Michael Medler and Aquila Flower from Western Washington University. And I'll give a shout out to Dr. Dorothy Hall, who's sitting with us, who made some major contributions to the snow analysis here. So my name is Donal Sean O'Leary III. I'm here to talk about some wildfire responses that we've seen in response to this changing snowpack. All right. Maybe I can't get the clicker to work. Oh, it's on the side. Maybe? No, I can't get it to advance. I'm sorry. Oh, there it goes. I can use the roller ball, I'll try that. All right, so as my colleagues have discussed here, we're starting to see lower snow depth throughout the winter, an earlier snow melt in the spring, and those mean that there's less water available to ecosystems that depend on snow, especially in the western United States, where over 70% of their annual water budget comes in the form of snow. Now, one of the big signals that we've seen out of this is that in most forested ecosystems, earlier snowmelt is leading to more wildfire. However, interestingly, in some high desert ecosystems, we're actually seeing that a later snowmelt is leading to more wildfire. So how does that work? What I'm going to do here is take a step back, talk about how we performed our analysis, and then pull out two important examples to share with you. So first of all, we know that wildfire is highly dependent on the type of vegetation that it's burning in. So what we see here is the western United States. I broke this into 28 ecological regions and about 40 different ecosystem types. So we have, on total, about 155 different habitats that we performed this analysis in. And just to kind of show you a zoom in of what this looks like, all these different colors here in the northern Sierra Nevada that I've pointed out are different vegetation classes. And this little gold star here, that is where Paradise, California is. I'll get back to that here in a little bit. One of our big contributions in terms of snow really opened up this analysis for us by allowing us to take a more detailed look at what's going on. So previous analysis of wildfire was kind of limited to these broad ecological regions defined in these black area outlines. And that's because the available snow data that we had was just pretty poor spatial resolution. It was really coarse and kind of blurry. So what we did is we took some satellite imagery and we looked at it day by day. And we identified when that snow disappeared for the spring, so when the snowpack melted off. So what we see here are in these kind of warmer colors, these reds and oranges. Those are places that melted really early in the spring. And these cooler colors are places that melted off much later in the spring. Now, if we do this for every year on record, about 15 years, we can then compare year to year and say, okay, for, say, Paradise, California, 2015 had an outrageously early snowmelt. We also have maps that show us when and where wildfires are occurring throughout the country. At that point, we can make a table. So for each one of these ecosystems, we listed what day of year that the snow melted and how much wildfire burned there that year. All right, I'm going to get a little bit technical here. We then perform what's called a Spearman rank correlation. So you rank the data in terms of the earliest snowmelt to the latest snowmelt, and you see how the wildfires stack up. So in this example, we're getting a lot more wildfire during these earlier snowmelt years. The advantages of this correlation are that it'll tell us the direction of the relationship that we're looking at, and it can also give us a confidence interval. So the two examples I'm going to share with you now, we are 95% confident that there is a significant relationship between snow and wildfire. So first, I want to go to kind of western Colorado, eastern Utah, and the Canyon country, and we're going to look at these green areas here. So these are Pinyon-Juniper Forests. Now, this might not really look much like a forest to you. What these are kind of bushy trees. They grow to be about 15 or 20 feet tall, and they're usually pretty widely spaced. Now, in these ecosystems, if you get a fire started in one tree on a normal year, there's not a whole lot for that fire to spread into. There's kind of really sparse, patchy grass here. So it tends to just kind of fizzle out. So what we think is happening here is on years with more snow, later snowmelt means there's more water in the ecosystem. That'll encourage vegetation to start growing in these spaces in between. Now, we've definitely seen this in good snow years out in the west. As the summer progresses, this vegetation dries out. So if you do get a wildfire that starts in one bush, now you have this kind of continuous blanket of vegetation that'll catch on fire, leading to big wildfires in these ecosystems. So that's how you can get later snowmelt leading to more wildfire. This is one of the primary novelties of our work. We haven't really seen this in the literature before, so I'm really excited to explore this further. However, something we have seen in the literature before, but this just kind of adds more fuel to the fire, if you will, is that early snowmelt is leading to more wildfires, particularly in places like the Sierra Nevada in California. So my colleague Bennett Murch is a wildland firefighter, and he shared these videos with us to help explain what's going on here. So this is a typical forested ecosystem in the Sierra Nevada, and this is what wildfire does in kind of a normal year, or maybe a wetter year. You get these ground fires that occur, and they'll start spreading throughout the forest floor. And you can see here that these larger trees, they're not catching on fire. They actually have pretty thick bark that's allowing them to resist fire from traveling up into the canopy. Now, these ground fires can persist for hours or even days and not really cause too much problem. This is actually a really important, healthy part of ecosystem dynamics in these forests. However, if you get trees that are really stressed out because of persistent drought, low snowfall, not enough water, that's when things get really bad. So this is a crown fire developing in these forests. And when a crown fire takes over, we can have some tragedies. So this is an image from another perspective. This is actually taken on November 9th of this year. This is the camp fire. It's called camp, and not just like a campfire that got out of control. What we're seeing here is up in the mountains of the Sierra Nevada, the fire actually started up here in the trees, and the wind then pushed it down slope into the Central Valley. So this is Chico, California down here, and you can't even see Paradise because it's being completely overrun by this wildfire. So our work was the first to identify a link between satellite-derived snowmelt timing and wildfire activity. And we think that this is an important contribution because for these ecosystems where we know we have a significant response, if we see low snow in April, land managers can start to prepare for wildfires that occur in November. That gives them about a 5-month heads up to get out on the ground, make some preparations. Now, one of the take-home points that I'd like to give for homeowners is that we do have good plans for how to prepare for wildfire. It all has to do with removing vegetation from around your home, and yes, even raking the forest if it is encroaching on your property. So that's all I have, and thank you for your time.
We're good. Okay, great. We will now open it up to questions from reporters in the room. Any reporters have a question? Please state your name and affiliation. Are there any questions?
Hi, good afternoon. Excuse me, good morning. Eric Neeler at Wired. I'm just curious if perhaps Amato or Zubin or anyone could give us a little bit of forecasting for where we're headed and in this century under some of the regimes that we're looking at under climate change, and what are some of the unexpected things that we may see?
I mean, as always, when you try to predict the future, it's always very dangerous. But from our research, we see the impact on snowpack from 2 factors. One is the precipitation, always substantial variability. One is temperature, and the temperature has 2 effects on snowpack. One is the partitioning of precipitation into rainfall and snowfall. Overall, with increased temperature, there will be less snowfall and more rainfall. And second, on the snow oblation, including the sublimation and the melt, increasing temperature will increase both. So with the global warming, we are going to see the increased percentage of areas across U.S., particularly over western U.S., in terms of significant decline in snowpack. At this time, we only see 13% from 1982 to 2016, but for the future, that percentage will keep increasing.
Yeah, I agree. There's a fair bit of literature out there looking at, model simulations, what's going to happen over the 21st century, and I think our results are in a sense, saying that, what people are suggesting we should be seeing over the 21st century is in effect already happening.
Are there any other questions from reporters in the room? Are there any questions on the chat? Okay, great. That concludes our press conference. Thanks so much.